Hello, let me explain our paper CG-NeRF, Conditional Generative Neural Radiance Fields for 3D-aware image synthesis. Recently, many NeRF-based generative models achieve the generation of diverse 3D-aware images. However, their applicability is limited because they cannot be incorporated with user-specified conditions such as text and images. In this paper, we propose a novel approach called the Conditional Generative Neural Radiance Fields, which generates multi-view images that reflect multimodal input conditions. To accomplish our goal, which is to synthesize view-consistent and diverse images by reflecting the characteristics of multimodal conditions, we designed a model that can generate diverse images with different fine details, sharing the coarse characteristics of condition inputs. As an input, the global feature factor extracted from the input condition is fed to the network along with the noise codes, randomly sampled from a Gaussian distribution. The main architecture consists of three components. First, a feature extractor that extracts global feature factors from the given conditions. Second, a generator network that creates an image by reflecting the conditions. And finally, a discriminator network that distinguishes real images from fake images based on the condition input and that predicts the camera poses of fake images for the PD loss. Next, let me explain the fine details of our generator network. The generator network consists of mapping networks, LMP blocks, and a CNN decoder network. The two mapping networks serve to generate the styles of the shape and appearance respectively, based on the global feature factor and noise codes. The MLP blocks encode style features using pairs of linear layer and activation function of feature-wise linear modulation. For computation and memory efficiency, after volume rendering the features in small spatial size, we utilize 2D CNN decoder network to upsample the features to RGB images at a higher resolution. To enable the generator network to produce semantically diverse images based on the condition input, we regularize the generator network with the diversity-sensitive loss. However, we empirically discovered that simply applying the diversity-sensitive loss causes undesirable effects that attempt to change not only the style, but also the pose of the output images. To address such an issue, we propose a pose-consistent diversity loss, which penalizes pose difference between images generated from different noise codes but from the same camera pose. The pose can be trained with the pose estimator network with the discriminator network by defining randomly sampled camera poses as ground truth. Second, to synthesize conditional outputs, we adopt a conditional GAN by training a discriminator that learns to match images and the condition feature factors. The total training object is defined with the sum of an adversary loss and our proposed pose-consistent diversity loss. Let me show you our experimental results. To the best of our knowledge, there exists a non-comparable previous work performing conditional generative NeRF task. Hence, we perform quantitative and qualitative comparison of a model with existing NeRF-based generative models to demonstrate the competitive performance of our proposed method. As you can see in the figure, our method shows competitive visual quality on cell A dataset. You can also refer to our experimental results on different dataset in our paper. To evaluate our approach quantitatively, we measure three metrics: the FID, precision, and recall. As reported in table, our method guarantees the most reliable performance compared to the previous methods. This is the qualitative results with various condition input types. For each condition type, the average output image generated with zero-value noise codes is visualized in the second column, and from the next column, we visualize output images generated from 5 different shape noise codes in the first row, and 5 different appearance noise codes in the second row. As you can see in the table, our method consistently maintains high visual quality across all types of input conditions. As a conclusion, we propose a unified architecture to generate diverse and photorealistic 3D-aware images by reflecting the multimodal condition inputs and effectively disentangling the shape and appearance from the input conditions. Also, we propose the pose-consistent diversity loss to produce various images while maintaining the view consistency. This is the end of our presentation. Thank you for listening.